Hello everyone, welcome to chapter 19, Planar Kinetics of a Rigid Body, Impulse and Momentum. In this module, we are going to discuss eccentric impact. Objectives is first to understand the definition of and mechanics of an eccentric impact, and then apply the eccentric impact analysis to problems involving impact of two rigid bodies. Now, in eccentric impact, usually we have the line connecting the center of masses is not the same as the line connecting the line of impact. So, for example, if I have two objects like these, so originally let's say my first object was like this, and the second object was like this, which is the two that we have in here. Center of mass is going to be this line, but the center of the impact line is this one. So impact, and this is center of masses, the line connecting centers of masses. If the two are not the same, then this is considered eccentric impact. So generally, let's say I have the first object A, coming at initial velocity va1. It will hit object B at point C, so at that point, let's say object B has an angular velocity omega b1, and just for the sake of analysis, I'm going to say that the point where A impacts B, I'm going to call it C, and velocity of C is related to omega by omega b1 times r, which is shown in here. Keep in mind, C is not the center of mass. So this happens before the collision. Now, once they collide, what will happen? Object A will give impulse on B, and B will give a reaction impulse on A. And these are opposite in direction, but equal in magnitude. And then what will happen? I will get velocity at maximum deformation. These two will be moving together, and this point will have the same velocity. So velocity of A at that point is the same as velocity of B at point C, which is related to omega by omega r. Remember, point C, velocity of C equals omega r, and velocity of C is the same as velocity of A in this instant. And then I'm going to get a restitution impulses, again, equal in magnitude, opposite in direction. And finally, each object will have its own final velocity. So object A will have VA2, object B will have omega B2. And again, velocity at point C, which is the point of contact between the two objects, will be related to omega by omega B2 times the radius r. So this is the mechanics of the impact. If I'm going to apply conservation of angular momentum, because impulses and the restitution impulses are opposite, they cancel, I'm going to end up with, this is general, regardless if it's 1 or 2. 1 is before impact, 2 is after impact. So HO generally will equal to MA, velocity of A, times R between A and O. Let me write it here to make it clear. So for example, it's going to be the distance. Point C is the same, remember. So it's going to be angular momentum, so it's going to be VA multiplied by the distance r. So it's going to be mVAR. Plus, now for object B, I have two things. I have IG omega plus velocity of the center of mass. Center of mass will have a velocity. Let's say VG2 here. So it's going to be MB multiplied by velocity G2 multiplied by a different distance r. So this is R, G, O, just to differentiate between the R of A and R of B. Now, in most problems, generally, the initial velocities and angular velocities of the object and the particles are known. VA1, VB1, omega1 are known. And usually the final velocity, VA2, VB2, and omega are unknown. Keep in mind that VB and V omega, they can be related by omega r. So basically I have only two unknowns. But this is only one equation. So how to come up with a second equation? We use, which is similar to particle analysis, if you remember, we use the coefficient of restitution. Analyze the problem before impact and during impact, and then during impact until after impact. Get the ratio of the impulses, and you get up with this expression. Okay, so coefficient of restitution is velocity of B to final velocity of B, and we call B meaning that this is at the point of impact. So this is velocity at, in our example, is velocity at C minus final velocity of A over, you switch them, so it becomes initial velocity of A minus initial velocity of B. So basically these are my two equations. Conservation of momentum around the point of rotation, and then coefficient of restitution done at the point of impact. And remember that V equals omega R. We are going to use this extensively. So let's start with the first problem. A 2 kilogram sphere moving horizontally to the right with an initial velocity of 5 meters per second. It strikes the lower end of an 8 kilogram rigid rod AB. The rod is suspended from a hinge at A, and it has an it was initially at rest, no velocities. Knowing that the coefficient of restitution is 0.8 between the rod and the sphere, determine the angular velocity of the rod and the velocity of the sphere immediately after impact. So first of all, let's draw the diagrams to analyze the problem to understand what I have. I have first of all the rod and I have the sphere. So the sphere was moving to the right, MS VS1. This is, by the way, fixed. So this is point A. This is center of mass G, and this is point B. Okay, and I have nothing else. At initially, the rod AB is at rest, so it is not moving. Then plus, what impulses do I have? I have the weight of AB, which is not impulsive, and I have the two reactions at the hinge. So AX, AY. So they do not give me any. They do not give me anything. So basically, they are non-impulsive forces. But this should equal after impact to. Now I will have the sphere. Now you might think that the sphere will go to the left after the impact. Yes, but just as an assumption, I'll always keep it. I can always keep it as positive direction. Okay, so this is my X, this is my Y, and I can do, this is my Z. So I can keep it positive if I want to. So this is point A, this is center of mass G, this is point B, and then I have now rotation, and it's going to be I omega, I AB omega 2, and also the center of mass will have a momentum, so it's going to be mg vg2, and here also B will have mb vb2. Okay, so this is what I have in this problem. Now system is conserved, therefore I know that H at A1 should equal to H at A2. That's all I need to. That's all I need to solve this problem. So let's start doing it. So I have H at A. What do I have? I have MS VS1 multiplied by the distance R, which is going to be between B and A. So it's going to be R B A. So it's going to be R B relative to A. The rod is at rest, so I have nothing there. Equals to, repeat the sphere. So I'm going to say MS VS2 R BA. Okay. Plus. Now, since the rod is going to rotate, I'm going to have velocity for the center of mass G. So it's going to be M for rod AB times VG2, okay, multiplied by R, G relative to B, plus I omega, because it's going to rotate. So it's going to be I AB omega 2. Okay. So now what I need to do is just to compute these quantities that we might need. Let's do the rod. IAB around the center of mass G equals to 1 over 12 M AB LAB square. So it's going to be 1 over 12. The mass of the rod is 8 kilograms and the length is 1.2. And this equals to this equals to 0.96 kilogram meter square. Okay. So now let's plug in the numbers. MS for the sphere is 2, initial velocity given as 5, and R between B and A is 1.2. This should equal, again, 2, and Vs is unknown, so I'm going to write R as 1.2, and then I have Vs2 as my unknown, plus MAB, which is 8, okay, R from G to B is 0.6, and then I'm going to write Vg, I'm going to relate it to omega 2. I want to make it in terms of omega. So Vg equals omega R. So it's going to be 0.6 square, okay, multiplied by omega 2, plus IAB, which is 0.96 omega 2. Again, just to clear this to you, I know from here that VG2 should equal to omega 2 RGA. So this equals to 0.6 omega 2. And since I already have 0.6 coming from this R, and I have another 0.6 coming from V equals omega R, that's why I have 0.6 square. And if I carry out this calculation, I end up with the following: 12 equals to 2.4 Vs2 plus 3.8 omega 2. And this is one equation with two unknowns: velocity of the sphere 2 and omega 2. Now, I'm going to apply coefficient of restitution. So we have E should equal to velocity, and remember the point of impact is point B. Okay, so we're going to start with VB2 minus VS2, over, you switch them, VS1 minus VB2. So this gives me coefficient of restitution was given as 0.8 should equal to, now instead of using VB, I'm going to relate VB with omega. So VB equals to omega 2 times R from B to O, which is the whole length, which is 1.2. So VB equals to omega times 1.2. So I'm going to write it as 1.2 omega, because I want everything to be in terms of the same unknowns. So 1.2 omega 2 minus Vs2, which is I don't know. Now, one thing, keep in mind, the minus is part of the equation itself. If it happens that, let's say I assumed that Vs was going to the left, then in this case, I will say minus Vs2. But I assumed Vs to be positive, so keep it as minus then Vs2. Over Vs1 is given to me as 5, and VB2 is 0 because it was originally at rest. doing this will give me the following relation that so this will give me that I can do 0.8 multiplied by 5 should equal to 1.2 omega 2 minus Vs2. So this is my second equation, and it has the same two unknowns, Vs and omega. Okay, that's why instead of writing Vb2, I wrote it in terms of omega. Solving these two will give me that omega 2 equals to 3.21 radians per second. It came positive, therefore my assumption of counterclockwise was correct. Okay, and then Vs2 came to be minus 0.143. So again, my assumption was that it's going to be to the right. It came out negative 0.143 meters per second, which equals to 0.143, to the left. So it's minus to the right, which was my assumption. Therefore, it comes 0.143 to the left. Okay? And this solves the two unknowns that I need. Now, let's go to another example. The mass center of the 3-pound ball has a velocity of Vg1 equals 6 feet per second when it strikes the end of the smooth 5-pound cylinder bar, which is at rest originally. Determine the angular velocity of the bar about the z-axis just after impact if the coefficient of restitution is given as 0.8. Okay, so let's start first by analyzing the problem. Basically, it looks something like this. If I'm going to say this is x, this is y, and let's say this is z. If you look upward, it's going to look something like this. Okay, so this is the center of rotation, and this sphere or the ball is coming in this direction. Okay, so we're going to call it we have the ball, and then we have the rod. So I can have that here. I have V. Sorry. So I'm going to have V of the ball coming ahead. So this is VB1, and this point is basically, we can call it capital B. So this is capital B. And the center here, we're going to call it Z for the Z axis. Now, the weight is acting perpendicular to the page, plus it's not impulsive. Reactions do not give me impulsive forces around Z. And the impulses between the ball and the end B cancel each other. Therefore, the system is conserved around the Z axis. So let me calculate first Iz, because I'm going to use it. So for the rod, it is 1 over 12 m L square. So it's going to be 1 over 12. The mass of the rod is given as, where is it? So 5-pound cylinder rod. So I'm going to say 5 over 32.2 to make it mass, multiplied by the length of the rod. So the length is given as 2 plus 2, so it is 4 feet. So multiplied by 4 square. And if I carry out this calculation, it comes down to 0.207. Okay, slug, which is the unit of mass, feet square. Okay, now I also I can find the relation between V, B, and omega, so that I'm gonna use it. I can do it differently. I can say omega 2 equals VB2 over 2. I'm just trying to solve it different than the previous problem to give you different options to see how things. Previously, the unknowns were the final velocity of the particle and the final angular velocity. Here I'm going to write it all in terms of the velocities. Okay, so what do I have now? I have h z1 should equal hz2. So what do I have? First I have the ball coming in at initial velocity, so it's going to be mb, and then velocity of the ball, it was vg, given to me as vg1. Instead of g, I'm going to use the same terminology, so I'm going to use it v ball 1 times r between b and z to make it angular momentum. Everything else is at rest, so I have nothing. This should equal to m for the ball, v ball 2, r from ball to z, okay, and that's it for the ball. So this is the first part. Plus, now the center of mass g coincides with the point z, center of rotation. Therefore, I have no velocity of center of mass. The only thing I have is I around z omega 2. So let me substitute the values. Mass of the ball was 3. The weight was 3, so I'm going to divide it by the weight to make it mass. So it's going to be 3 divided by 32.2. VB1 was given as 6. And the radius is basically this distance, which is 2 feet, was given to me. This should equal to, repeat the same thing for the sphere or the ball. So 32.2 multiplied by r, which is 2, and then the velocity is unknown. So I'm going to write it VB2 as my unknown. Okay, plus Iz, we already computed it to be 0.207. Now, instead of writing the unknown as omega, I'm going to write it as VB2. So I'm going to write omega as V capital B, point B2 over 2. Okay? So I'm going to write it in terms of capital B. So this is my first equation with two unknowns. One, final velocity of the ball, and final velocity of point B. Okay. Now, let's apply the coefficient of restitution. E equals to velocity of capital B2 minus velocity of the ball 2 over, you switch the initial velocities, VB1. And this will give me 0.8 equals to VB2 is unknown. So now, previously, in the previous example, we converted this VB2 into omega. Now, since I have it as an unknown, I'll keep it. VB2 minus VB2 was unknown for the ball, small v, small b. Then VB1 was given as 6, and everything was at rest. And this is my second equation. Solving 1 and 2 yields the following values, that B2 for the ball equals to 2.143 feet per second. And it gives me that capital B, the velocity at the point capital B, equals to 6.943 feet per second. Now I can use this to find omega 2, which equals to VB2 over 2, okay, which will give me the value of omega to be equal to 3.47 radians per second. Okay, so it's just a different way to show you that either you convert this one to omega, or you keep this one as VB and convert this omega into that point. So you have two options that you can do it, either this way or that way. With this, we solve this problem, and I conclude this module and this chapter. And I wish that it was useful to you, and I wish you the best of luck. Thank you.